Hello everyone, the problem that we're once again looking at today is the USACO 2019 February contest gold problem 2 of dishwashing. And if you haven't already, I strongly suggest watching the previous video on the same problem but on how to solve it in n log squared complexity if you haven't already. And the link to that video will be posted down in the comments below. And today we're going to be exploring how to solve this problem in n log n and even linear complexity. So you can pause the video first and look at the problem yourself if you haven't already in the previous video. And then think about it. Maybe give it a try. Maybe you can solve it in log n complexity too. Alright, so yesterday we've already explored the log squared complexity, in which case we binary search what is the size of the prefix that we can get in order. And every time we just take away the smallest in this prefix and then see if it works, right? And that's, even though that's pretty straightforward and was able to pass, it was quite slow. My experience with that is I submitted it multiple times and the average is around 1200 seconds, basically 1200 milliseconds, which is fast enough but can be faster, because as you can see with the linear solution it was able to run with the slowest being 77 milliseconds, and that's what I'm going to be explaining today. So first of all, with the method yesterday, basically what we did is we actually made the stacks. We actually made the stacks like that. This represents the center table, right? And then we recorded what's on top of every stack and on bottom of every stack. And now we found the first stack with label that's greater than the current one. We're going to indicate the green one. So basically we found the first one, this label is greater than the green one, and this label is smaller than the green one. So then we make sure that everything before it will be taken before this current one, and everything after it will be taken, and everything after it has a bigger label. However, we realized that we can actually make some improvement to that. We can make some optimization to that method. Because right now I've already written out a situation in which a conflict will happen. The current plate is I, and we have a stack right here with the top being X and the bottom being labeled Y. And when I has greater label than X, however less label, smaller label than Y, we have nowhere to put I. Because say we put I up here, it has greater label than X, so I is going to be taken before X, while X has a smaller label, and that's illegal. And if we put I on top of Z, which is a stack after the stack of X, then it's not going to work either, because I is less label than Y, so we had to take I before we take Y. So this is what we described as a conflict of the two rules that we stated in the previous video in the n log squared complexity solution. However, in the old solution, in this situation, we just returned 0, right? We just returned 0 with the check function and just said that you go to the next mid in the binary search, right? This middle value does not work, and now you move the R to mid, and then you binary search a smaller mid, right? That's what binary search is. However, we realize we don't actually have to do that, because what we can do now is, instead of saying we should have removed the element earlier, we can just remove all of these elements and every element before it. Because by doing that, we then allow, after removing every single element here that has value of less than I, this will be the first element with value greater than I, and then we just put I right here, right after removing all those. I know the drawing is kind of messy, but I think you get what I mean. Because now, basically, I is stuck somewhere between here, so what do? Well, we just remove everything above it, and then put I where it's supposed to go, right? And now we know when our answer is found, when something doesn't work, when we receive an I with values smaller than the greatest one, the maximum one that we already removed, right? Because in that case, whenever we remove I, it's not going to work, because the maximum that we removed is already greater than I, and it's not going to be able to be in the same order. So knowing that, now basically every time what we've got to do is to find a stack like this, if there exists one, and we remove everything on the stack and on the stacks before it, and then put I there. And removing it, we're also in that process recording the maximum plate label that we have already removed. So doing this allows us to actually solve this in n log n complexity instead of log squared, because we don't have to binary search anymore. Now all we binary search is this stack, the label of this stack, and then we can just start removing stuff and putting I on. However, we can optimize this even further, but this time it's going to be purely programming. It's not going to be a lot of theoretical stuff like the optimization of n log squared to n log n. So first of all, let's take a look at the code in n log n complexity. This code actually runs in ON linear, but I still have the n log n code right here commented. So obviously input, and then we just go from every 2 to n because we had to make the first stack LM and RM, and each time if the maximum review removed have bigger label than the current one, well, we know there is no way we can remove AI while still preserving the order, so we break. And otherwise, we binary search the first spot that has plates greater than I, which is going to be either this stack, or if there's not a stack where I is stuck between, it's just going to be a stack right here. We can just put I on top of it, which is the perfect situation, because that way we don't have to remove anything. And then we remove stuff if we need to. That's just removing everything on that stack and the stacks before it, and then we put I onto what's remaining of that stack. This solution is going to have a log-n complexity because of the binary searching process of finding this proper stack to remove and put I on. However, we can actually eliminate that log-n complexity by doing a pretty smart trick, I would say, by the solution. So the first thing I would do is that for every stack, we don't actually have to number 1 to n. That's just dumb. We just number them according to the bottom place label, right? Whichever place started the stack, we're just going to call the stack the label of that place. And then notice that every plate I will always be placed on the first stack to be created out of all stacks with bottom label greater than I. So take a moment to process that, but I think it should be quite easy to understand because we know every single place with label greater than I is going to be placed also on this plate with the first being placed with bottom greater than this current plate. Right? You can just take a look at this paragraph right here. I think that explains it pretty well. All plates greater than the bottom of that stack, call it bot, and smaller than I, which are the plates that we want to place I on top of, right, will be placed on bot, the stack bot. So all we've got to do is remove all plates on stack bots that are less than I and then push I on the stack bot, right? So from that we know that we can actually easily find which stack we're looking for this I without even using binary search, because all we've got to do is, as my code did right here, set the base of every single j with value less than the current I. If this I created a new stack, we set the stack that this j is supposed to be on to I. So from now on, we say if there's any j that exists later with value less than I, we place it on stack I. Right? That's if I has its own stack. Maybe AI doesn't even have its own stack, right? And now we're able to find which stack every plate is on just based on the base array that we already have, right? And obviously, if base j is not already 0, that means we already have a stack with greater bottom label than j, and then we just break, right? Because we always place it on the first one, the first stack to be created with bottom label greater than it. And then even though there's a while loop here, it's actually every play will only be popped once, so it's still linear complexity. And this program allows our submission to be ran under time of 77 milliseconds, which is really good considering that the original nlog squared had 1200 milliseconds. So now let's come back to the question today. And basically the trick that we did today is realizing that we don't actually have the binary search, because every time that we see a conflict, we don't just return 0 like the binary search check function. We just remove all the place that does not satisfy the constraint, and we still place I. And once we see a plate that's greater label than the maximum one that we already removed, well, obviously there is no way to remove it in proper order, and we just break, and that's our answer. And the way to solve it in linear complexity is by realizing that every plate will only be placed on the first stack to be created out of all the stacks with greater bottom label than itself. And that allows us to solve this problem in linear complexity. Hope this video helped. Thank you for watching. Alright, that was a problem for today, and it was a pretty good problem actually. I've never actually, I think, had 2 videos just for one problem, and this one's not even that hard. It's just there was 2 different methods and 2 different complexities, and one of them I was able to come up with during contest, so I still wanted to share it, while the other one is way faster and way smarter. So now we're done with the problem review. Let's take a look at the grind report. Today's grinding was, okay, it was like meh, it was mid. Basically what I did was I mocked the 2021 US Open contest gold, and got cooked. I was able to solve this one rather quickly. In 35 minutes, I'm pretty sure, which is really surprisingly fast for this difficulty, especially considering that I was not able to solve either of those during contest after solving that. Portals was able to be solved by me after I was done with the mocking. Actually, I didn't even finish the mocking. I mocked when there was I mocked for 2 hours and 20 minutes and just gave up on the second two and just looked at solutions. And I realized Portal is not even that hard. It's just cruise code shortest spamming tree, minimum spamming tree. And I really should have noticed that, but I was not able to make the important observation that when you switch a vertex, you never make the two unconnected. Like at first, I was thinking about how like if you add an edge, you have to erase an earlier edge, and this just makes everything so much more complicated. However, a key notice is that when you add a new edge, it actually never makes two. It does erase the node edge, but it never makes 2 points unconnected. The 2 points that we break apart from adding this new edge never becomes unconnected after this. They're still going to become connected as long as the final shape that we make is a tree. And that's a property of minimum spanning tree. It's always going to be a tree. So from that, we know that we don't have to worry about erasing edges. Just add them. And it's just literally standard cruise count. So I was able to solve that after looking at the solution. And the last one was just way too hard, but I'm still going to explain it a little bit. I did not even write a code for it because it's very difficult. But basically, the key observation here is that the shape is always a triangle. And it's always a triangle, a big one, with some smaller triangles stuck inside of it. Because think about it. If we have a triangle right now, and say if we say add a point right here, right here, then it's inside and it's going to be connecting 3 points to the three vertex of the smallest triangle that includes it. Right? Think about it. If we have like a P6 right here, it's going to connect to P4, P3, and P2, obviously. And if we have any points outside here, it's only legal if we can connect it to all three vertices of the largest triangle. And if it's like over here, then it's obviously not going to work because P1 is blocked. So knowing that property is actually makes everything way easier because now if we do DP, the only thing that we have to record in our state is the coordinate of the biggest triangle. And if like the new spot that we're trying to transfer for the DP state is inside the triangle, we know it's gonna work. And if it's outside, we just check if one of the vertices blocked, and otherwise everything works. And that's gonna get us to n to the fifth power solution. However, the solution offered an n to the fourth power solution because here n is 40, so n to the fourth is obviously gonna be a lot safer considering n to the fifth is I'm pretty sure 1.25 times 10 to the eighth, which is very dangerous. But if you're good at constants, you should be fine. But n to the fourth is way better. And in this case, the solution using n to the fourth is going to be we transfer state backwards. So we only keep track of the three angles location and we don't keep track of what eye we're on right now. And every time we just try to transfer from any point inside this triangle and basically I didn't really actually understand the n4 solution, but basically I'm pretty sure what it's saying is we transfer backwards, we only record the three angle coordinate, and then we try to transfer with any point inside of it. I did not actually understand, but this is a really difficult problem. It's gold, it's US Open, and it's the last problem. Even though it's 2021, I would say it's hard, and it's harder than I probably could do. And I really should be doing a lot more silver problems than gold right now, with the contest being literally 15 days away. So then after mocking that not actually even mocking, after doing that contest, I went to the 2019 US Open and solved the last silver problem that I was not able to solve. Left out, I solved a few days ago. Cal steeplechase, I was never able to completely solve. It's sweeping line, way too complicated. Computational geometry, I hate computational geometry. And fence planning is so easy. I don't know why it was that easy. Look at the complexity of the complexness of the other two problems, and you would just think this is so out of place. Like, why is this problem here? It's way too easy. It's bronze. It's like bronze 2011 level. That's like insulting to this problem, but that's what I think of it. I looked at it and I was like, are you serious, dude? This problem on the US Open with the other two problems being that difficult? Are you serious? That's literally what I thought. And then I solved it. Within 10 minutes, I would say, I think, yeah. So yeah, that's it. So basically today, combining the mock contest and this problem, it took me a total of 4 hours because obviously this one took me 10 minutes. So, and yeah, it was good, better than yesterday, but yeah, it could be better. All right, with 15 days left, I'm cooked, and yeah, I'm basically cooked, but I'll still try it. All right, thank you for watching this video. See you tomorrow.